Welcome to the AquaGate security series. Over 4 videos, we are going to attack a deliberately vulnerable web application and then fix it. This first video covers session hijacking, 3 different ways an attacker can take over an authenticated session without knowing the victim's password. AquaGate is a fictional waterway lock navigation portal. Vessel operators submit passage requests. They say which lock they want to pass through, when, and with what vessel. Port administrators manage the lock schedule and approve or deny requests. It represents the kind of internal tooling you would find in any organization, a typical web app with a login page and an admin panel. And it has 7 security vulnerabilities deliberately baked in. HTTP is stateless. The server has no memory between requests. Sessions are how we give it memory. When you log in, the server gives you a signed token stored in a cookie, and your browser sends that token on every subsequent request. Flask stores session data inside the cookie itself, signed with a secret key. Every session cookie has attributes. HttpOnly prevents JavaScript from reading it. Secure requires HTTPS. SameSite controls whether the browser sends it on cross-origin requests. We will see exactly what happens when these are missing. 3 techniques in this video. First, steal the cookie by injecting a script, cross-site scripting. Second, exploit the absence of session rotation on login, session fixation. Third, replay a captured cookie from a different client, session replay. Each one assumes the previous layer of defense is absent. Together, they paint a picture of what proper session security actually requires. Vulnerability 1, cross-site scripting, specifically reflected XSS. The attack works in 3 steps. We inject a script via a URL. The script runs in the victim's browser and reads document.cookie, and it sends that cookie to our listener server. Let's see how the application makes this possible. Here's the search route in the insecure version. The user's query string is taken directly from the URL and injected into a template string using Python's % operator. Render template string then evaluates it as live Jinja2 template content. The key problem: % substitution happens before Jinja2 sees the string. Anything in the query, including HTML tags and JavaScript, becomes part of the template source. In the secure version, render template is used instead, passing the query as a safe template variable. Jinja2's auto-escaping handles it correctly. Let's run this live. I have the insecure version running on localhost 5050 and an attacker HTTP listener running on port 8888 in a second container. We'll start by showing normal search behavior, then inspect the cookie flags, and finally deliver the XSS payload. Here's the AquaGate portal running normally. The search feature lets operators look up lock status. Let's search for lock 4, a legitimate query. Normal results. Now let's open DevTools and look at the session cookie before injecting anything. The cookie is visible in DevTools. Notice the HttpOnly column. It's unchecked. This single missing flag is what makes cookie theft possible from JavaScript. Now let's deliver the XSS payload. The XSS payload is in the URL. The script tag we injected executed in the browser, reading document.cookie and redirecting to our listener with the value appended. The browser navigated away from AquaGate entirely. The attacker listener logs confirm the cookie arrived. The full session value is in the query string, prefixed with C equals. This happened entirely in the victim's browser. No server interaction was needed beyond the initial page load. This is the normal search page working as intended. Notice how a legitimate query returns lock results cleanly. Now let's look at the cookie before we inject anything. DevTools is showing us the cookie attributes. HttpOnly is false. That single column is all the attacker needs. If HttpOnly were checked, document.cookie would return an empty string. The script we're about to inject would have nothing to steal. We've injected a script tag into the search query. The application reflected it back without sanitizing it. The script executed in the browser, read document.cookie, and redirected to our attacker listener with the cookie appended as a query parameter. The browser is now showing the attacker's server. And here it is in the attacker server log. The full session cookie value delivered over HTTP to our listener. An attacker now has everything they need to impersonate this user. No password required. Vulnerability 2. Session Fixation. This is about what happens, or rather what doesn't happen at the moment of login. Proper session management requires generating a fresh session token every time a user authenticates. AquaGate skips this step. In the insecure login route, credentials are validated and session data is written directly. No session.clear call beforehand. In Flask's signed cookie model, this means the encoded session payload is the same every time you log in with the same credentials. In the secure version, session.clear is called first, ensuring a fresh token on every login. Let me show you what this looks like in practice. I'll log in twice and compare the session cookie payloads side by side. Now the session fixation demo. I'm logged in as Vessel Op. I'm copying my session cookie. I'll log out, log in again, and compare the payload segments of both tokens. Second login, new session cookie. But look at the first segment, the encoded payload. It's identical to the previous session. The timestamp and HMAC differ, but the session data itself was never rotated. Here are two session cookies from two separate logins. The first segment, the encoded payload, is highlighted. It's identical across both sessions, different timestamp, different HMAC signature, but the same payload. The absence of session.clear means pre-authentication state is never wiped and the session data is never rotated. The fix is one line. Session.clear before writing authentication data ensures the payload is always fresh at login. In the secure version, that single call closes the fixation window entirely. Vulnerability 3. Session Replay. We've stolen a cookie via XSS. Now let's use it. This vulnerability combines three missing protections. No HttpOnly means the cookie is readable by JavaScript. No SameSite means it can be sent by external clients. And the application has no mechanism to detect that the same token is being used from a different context. 3 cookie attributes, all set to their insecure defaults. Session cookie HttpOnly is false. JavaScript can read the cookie with document.cookie. Session cookie secure is false. The cookie travels over plain HTTP. Session cookie SameSite is none. The cookie is sent on cross-origin requests. In the secure version, all 3 flip true, true, and strict. 2 things to demonstrate: reading the cookie live from the browser console, then replaying it from the command line as a completely different client. No browser, no login form, no password. Now the replay attack. I'm logged in as Vessel Op. I'll use the browser console to read document.cookie. This is exactly what the XSS script did. Document.cookie returns the full session value directly in the console. No special tools needed. It's a standard browser API. Now I'll copy this value and replay it from curl after logging out. Logged out. Browser shows no session. Now I run curl with the stolen cookie value passed via B flag. The server has no idea this request isn't coming from the legitimate browser session. The session cookie is fully readable from the browser console using document.cookie because HttpOnly is not set. We then copy that value and replay it from curl. The server accepts it, returning the full dashboard response. Authenticated access, no login required. 3 attributes, 3 protections. HttpOnly. JavaScript cannot read the cookie. The XSS payload runs but has nothing to exfiltrate. Secure. Cookie only travels over HTTPS. SameSite strict. The browser won't send the cookie on cross-origin requests. These don't eliminate XSS. That requires fixing the template handling, but they contain the blast radius significantly. Quick summary. HttpOnly stops JavaScript from reading the cookie, closing the theft vector. SameSite strict stops cross-origin replay. Session.clear on login stops session fixation. Using render template with proper variable passing instead of raw string substitution stops the XSS injection entirely. Notice these are layered. None is sufficient alone. Defense in depth means each layer assumes the others might fail. 3 vulnerabilities down, 4 to go. V1, reflected XSS, open. V2, no session rotation, open. V3, missing cookie flags, open. In the next video, we go below the HTTP layer entirely, from cookie theft to an interactive shell inside the container.